So today we discuss a current carrying coil as a magnetic dipole. Okay. So previous class we discussed what is a magnetic dipole and what is magnetic dipole moment. So this class is little bit lengthy. Okay. So that's why I skip a very small part. Okay. That small part is the current carrying coil as a magnetic dipole. That small part we discuss today's class. Okay. So you know that the concept of what is a magnetic dipole and magnetic dipole moment. You know that concept from previous class. Here we discuss a current carrying coil as a magnetic dipole. A magnetic dipole. Okay. So actually you know that the field produced by a current carrying coil produces a field. Okay. And such coil behave as a magnetic dipole. Okay. So here we know that tau, the rotating vector, tau, that is a moment, magnetic dipole moment cross magnetic field. We derived this equation previous class. Previous class we derived that equation. And here main important concept is that field produced by a current carrying coil, field produced by a current carrying coil, okay, and such coil behave as a magnetic dipole, and such coil, these coil behave as magnetic dipole. So from this understanding, there is a coil, and there is a current direction. Okay, and we know that magnetic moment and current, we apply the right hand thumb rule here. Okay, so with the help of right hand thumb rule, we define the direction of mu, magnetic dipole moment. So thumb represent mu and other forefinger, curl of other forefinger represent current. So here that's the other forefinger, that is a thumb. Okay, so thumb represent moment mu. So this is the moment direction. And if this current produces a magnetic field. So field direction also will help that right hand thumb rule. This time the thumb represent current. So here the thumb current and curl of other forefinger. If I grab the wire and thumb represent the direction of current and curl of other forefinger, this other forefinger, here thumb represent current, curl of other forefinger represent magnetic field. So here the field is this direction. So it look like this direction is field B. And you know that a bar magnet, if I place an imaginary bar magnet here, yes, a imaginary bar magnet here, bar magnet here. So field release from that pole and ending from that pole, and you know that field is released, that's north pole, and field enter in south pole. So this is we have as a bar magnet here. Okay, actually, and similarly B direction also, this direction also satisfy the B. Clear? Okay. Now we calculate here the magnetic field of a coil. calculate magnetic field of a coil. Okay, so there is a coil. Current carrying coil is look like this. Suppose you draw a current carrying coil. Okay, that's a current carrying coil. Suppose that is a direction of current. So that's here the dot. So that means cross. Okay, and that is length, small length be the ds here. Okay, and from center, this is a half circle actually. The center, calculate the magnetic field at this point P. Okay, that's a very small length, and this is a R, and there is a capital R here, radius, and that is a Z from center of that loop. Okay, so calculate BP on that axis of the central circular path, central circular line. So here dS, this current produces a magnetic field, and that magnetic field in that direction B. Okay, B, and the direction is suppose as R cap direction. Okay, and we find from that B with the help of Barlow-Savart's law, and that suppose the angle be here, this angle be 90 degree, and suppose we choose that angle be the alpha. Okay, so there is a two component of B, that is a B perpendicular, dB is a perpendicular to that axis of the central, okay, circular path, and here is a D parallel, dB parallel. If this angle be the alpha, that is the 90 degree, suppose this angle be 180 equal to 180 minus alpha plus 90. So this angle be the, sorry, bracket open, here is the 90 minus alpha, this angle be the 90 minus alpha, 90 minus alpha. Okay, so that's the 90 degree, that's the 90 minus alpha, and suppose we know that the angle be the x. So 90 minus alpha plus 90 plus x, we get 180, because that is a straight line. So here 90, 90, 180, 180, 180 cancel, so x equal to alpha. So we finally get this angle be the alpha, this angle be alpha. Okay, so it's that angle be alpha. Okay, remember that's angle be x be the alpha. So we know that B with the help of Barlow-Savart's law. So B we know that is a dB, okay, and that is a dB, that is equal to mu 0 by 4 pi I. Here the ds length by times sine 90 degree by r square. These are r square, and sine 90 be the 1, so you get dB equal to mu 0 I ds by 4 pi r square. That's the dB. But actually the calculation that dB parallel, and dB parallel is that obviously these are the component of B cos alpha. If I say that is the x component, that's the y component, and that's angle is, so the B x component of B, that is dB parallel to that line, obviously. So B cos alpha. So here the dB cos alpha. So final calculation is the dB cos alpha. So we know that dB dB equal to mu 0 I ds by 4 pi r square, and cos alpha, so that is a base by hypotenuse, r by r, that's the cos alpha. Now solving that ds with the help of integral dB parallel integral, and say that is dB parallel b. If I say that is a final b, obviously. Okay, say that is dB parallel equal to b. So the b equal to mu 0 I capital R by 4 pi small r cube integral of ds. So we get final answer is mu 0 I capital R integration of ds, we get s by 4 pi r cube. So r cube, that's the r is the hypotenuse, that's the base, that's the perpendicular. So Pythagoras theorem, we know that r cube, that is equal to capital R square plus z square, root means half, that is 3 by 2. And these a's, okay, that's the circumference, is not actually ending here, that's a complete path. I draw the half, this is not half here, that's the full circle here. So that is the circumference. So mu 0 I r, that's the radius r, so circumference of the circle we know that is 2 pi capital R by 4 pi r square plus z square whole to the power 3 by 2. That's 2 pi, 4 pi cancel the 2. So final answer we get b equal to mu 0 I capital R square by 2 r square plus z square whole to the power 3 by 2. That's the final expression of magnetic field. It's going to be a Tesla. Okay, that's the final expression we find. Now, if that here is a apply condition here, if z, okay, if z is very large than r, so here if z is very greater than r, larger than r, so there will now be change in that b, that is equal to mu 0 I r square by, so ignore that these are, so we get 2 z 2 times 3 by 2, we get 2 to cancel, so we get mu 0 I capital R square by twice z cube. Okay, now that is mu, that is suppose that is a n put here, the number of turn in coil. So there is not a single turn, there is a 10, 2, 3, n number of turn here. That is the n number of turn. So n is the number of turn and given coil. So we get n, and there is a multiply by pi capital R square and 2 pi z cube. Okay, so pi r square means the area, this area. Okay, these are the area. So area of circle, that is b, we finally get mu 0. So here, sorry, I get I n a, that's the area. Sorry, that's the area A by 2 pi z cube, and INA, we know that INA from previous class, that is equal to mu equal to INA. So finally we get B equal to mu 0 by 2 pi. So INA replaced by mu, that's a vector B by Z cube. That's the final expression of magnetic field. Okay, and the direction of the B is Z direction. So Z. Okay, the current carrying coil due to current carrying coil. Okay. The two ways the current carrying coil have a magnetic dipole. There are the two ways. Okay. There are two ways where current carrying coil have magnetic dipole. Have dipole. Two ways. So way number one is first way at experience torque when we place in an external field. Experience torque when we place an external field. We place an external magnetic field. Okay. Current carrying coil place an external magnetic field B. That's also behave as a dipole, magnetic dipole. And way number two, generate own intrinsic magnetic field. That is, generate own intrinsic magnetic field. Okay. So given the distant point along the axis, given that's actually that calculation. Given distant point along its axis. These derivation. Okay, clear? A very small topic, magnetic field of a coil, and here's a current carrying coil as a magnetic dipole. Okay, so today end the class here. Next class we discuss moving coil galvanometer. Okay, so galvanometer sometimes treated as an ammeter and sometimes it's treated as a voltmeter. Okay, next class we discuss the concept of galvanometer. Okay, thank you.